The vapor compression refrigeration system is nearly 200 years old, but it does not seem ready to leave the scene anytime soon. While some people have viewed this method as environmentally harmful and inefficient, the cycle is still applicable in the industrial sphere. Natural gas plants, petroleum refineries, maritime transportation, petrochemical plants and most of the food and beverage processes are some of the industrial plants that utilize vapor compression refrigeration systems. Refrigeration may be defined as lowering the temperature of an enclosed space by removing heat from that space and transferring it elsewhere. The vapor compression refrigeration system involves four main components: compressor, condenser, expansion or throttle valve, evaporator. Beside the main components, additional devices are equipped into the system: oil separator, liquid receiver, filter, sight glass, suction accumulator. The compressor is the mechanical heart of a refrigeration system. Refrigeration compressor is generally a piston reciprocating type. Larger systems have multiple cylinders with an unloaded system, using the suction pressure as its signal. The low-pressure refrigerant vapor is sucked by the downward stroke of the piston from the evaporator discharge. The upward movement of the piston compresses the vapor, which leaves the compressor at a different pressure, and the extra energy applied on it causes strong superheating of the refrigerant vapor. The most common type of condenser, used in marine refrigeration systems, is shell and tube type condenser. The refrigerant flows through the shell, while water flows through the tubes, in single to 4 passes. There might be a vent connecting the receiver to the condenser for a smooth drainage of liquid refrigerant. The shell also acts as a receiver. Further, the refrigerant also rejects heat to the surroundings from the shell. The most common type is horizontal shell type. The thermostatic expansion valve is often shortened and cooled, just thermal expansion valve. Both of these names are a bit long, and engineers like to find shortcuts. So, I'll often just use the acronym of TXP or even sometimes just TEV, depending on where in the world you are. The main components inside the thermostatic expansion valve. If we pull apart a thermostatic expansion valve, and we're going to see the following main components. The valve body, which holds the components, and has an orifice inside to control the flow of refrigerant. And we have the diaphragm, which is a strong, thin, flexible material, typically metal, which flexes to apply pressure. And we have the needle or pin and seat. This moves up and down to restrict the refrigerant's flow path, the spring, which counteracts the force of the needle. And we've also got the sensing bulb, and the capillary line, which causes the valve to open or close. So how does it work? The expansion valve, it's just before the evaporator, and holds back the high-pressure liquid refrigerant from the condenser, controls how much refrigerant can pass into the evaporator. The valve decreases the pressure to allow the refrigerant to boil at lower temperatures. This mixture of liquid vapor refrigerant is sprayed into the evaporator. Well, it will absorb heat from the refrigerated space, which surrounds the pipe. In this example, the fan is blowing air across the evaporator. As the refrigerant passes through the evaporator, and it is exposed to more thermal energy, it will cause it to undergo a complete phase change, and will then become a saturated vapor, towards the end of the evaporator coil. During this change, there will be little to no temperature change, because of the latent heat, and instead it will increase in entropy and entropy. The refrigerant will continue to pick up thermal energy. And when it does this, after the phase change has occurred, it will then start to increase in temperature. This superheat the refrigerant vapor. And the sensing bulb of the expansion valve is monitoring this temperature to control the refrigerant. Let's say the cooling load increases. This will cause more refrigerant to evaporate, and the superheat will increase, causing the refrigerant temperature to increase at the evaporator exit. We need to decrease the superheat, and we can do that by allowing more refrigerant to flow into the evaporator. So the pin will need to open more, to let the refrigerant pass through. Inside the sensing bulb, is a small amount of refrigerant, which is separated from the rest of the system, and constrained in a closed system to the area of just the bulb, the capillary tube, and the power head. The sensing bulb detects a temperature increase, which causes a small internal reservoir of refrigerant to boil, and evaporate. Because the refrigerant is constrained to a small area, it will cause the pressure to increase, and this pushes along the capillary tube up to the top of the expansion valve. This pushes down on the diaphragm, and that pushes down on the pin, which compresses the spring and allows more refrigerant to pass through the orifice. The valve will adjust to find the correct position, so that the force in the diaphragm is greater than or equal to the force of the spring, pushing in the opposite direction. This allows the correct amount of refrigerant to flow, which decreases the superheat refrigerant temperature at the outlet, and the sensing bulb detects this and equalizes it. If the cooling load then decreases back to normal, the superheat temperature will reduce. The sensing bulb will detect this, and will begin to reduce the refrigerant evaporation in its chamber. Refrigerant in the capillary then flows back towards the bulb, and the main valve begins to close. The superheat temperature will also start to rise as this happens. Eventually, the valve equalizes out, and the correct amount of refrigerant will flow through to match the superheat settings. Now all of this happens automatically, using this type of valve, which is why it is so popular. The oil separator maintains a high coefficient of condenser and evaporator performance by almost completely removing oil deposits from their exchange surfaces. The oil separator consists of internal baffle plates, arranged along the path of refrigerant, as the refrigerant flows through the separator. The baffles will rapidly reduce the gas speed and create the conditions required for the separation of the oil from the refrigerant. As the oil is heavier than the refrigerant, it gets collected at the bottom of the separator. The bottom portion is provided with outlet pipe, which is connected to the section of oil compressor crankcase. There is a floating operated needle valve arrangement, which opens the valve once set level of oil reaches inside the separator. The bottom of the separator may be provided with permanent magnet, which will hold all the metallic impurities, which may stuck the needle valve, or can damage compressor internal parts. Liquid receiver. The refrigeration system provided with an expansion valve are often equipped with liquid receiver, built to withstand high pressures. The functions of the liquid receiver is to 1. Separating the refrigerant vapor, to prevent its transmission to the liquid line. 2. Receiving the liquid refrigerant in the condenser through a drip tube, it pulls the liquid near the bottom, and towards the expansion valve. 3. Stores liquid refrigerant during any maintenance shutdown.